Hello. All right. So let's recap what we did last time. We managed to make a neural network that could classify handwritten digits with 95% accuracy. I understand almost all of how it works. Which is by, it's a network of sigmoid neurons that has 784 neurons in the input layer, 30 in the hidden layer, and 10 in the output. The weights and the biases of the neurons are encoded in a weights matrix and a bias vector, or a list of weight matrices and a list of bias vectors to do the forward propagation. So in order to check, you pass in an image and you get out a prediction. You just do the multiplications by the weights, you add the biases, and then you take sigmoid of that. You do that for each neuron, which means you can do the whole thing as a matrix operation. And then you do it for each layer until you get the answer. When you want to train, we want to figure out the direction of the gradient of the cost function with respect to all of the weights and all of the biases. And then we want to move by a small amount, which we'll call eta, in that direction, or in the negative of that direction. So we want to go in the direction that minimizes the cost. So in order to do that, we take our training data, we look at a little piece of it, so some number of examples, and then we update our weights and biases in accordance with the direction that would make the cost better, like as in lower for those examples. How do we update our weights and biases? So we figure out the gradient of the cost function with respect to W and B. For each example, the gradient changes a little bit. And then once we've collected up all of the changes that we want to make, we make the changes by moving in that direction by eta over the number of examples that we moved, that we were using. The only thing that's still mysterious is how do we actually figure out these gradients? And I understand this a little bit. Some of this I understand, I should say. So we're going to be figuring out these z's and these x's. Z's are the inputs to the sigmoid function. So these are also called the weighted, I forget what he called them, the weighted inputs or something like that. So this is weights times input plus bias, and then you pass that into the activation function, which for us is a sigmoid function. And then these are the outputs at each layer. And you know, that counts in the first layer, that means it's just the input. So it's like there's a fake layer before the network starts whose output is the input to our network. So we can calculate these by just going forwards and adding this stuff to the, or by, like, we have to calculate these in order to get the output. So we just go forwards and we remember these as intermediate values within the output. Something I wanted to do that is like really not necessary is this thing here, just to save 2 lines. I actually wonder if that works. Is there, or clear, Python main. Can you do a walrus operator when you're not defining a variable for the first time, but you're reassigning it? Yes, because this is still working. Okay. Yeah, it's interesting that we only jumped to 81 when before we could jump to 90 on the first iteration. But that's not because of this, that's just because of randomness. Okay, so I understand how to figure out these things. Then we want to figure out the actual gradients. Oh wow, big jump in the 8th epoch. Then the rest of this is a little harder to understand, but some of it I understand. So for example, grade CA, this should be of L. So this is the last layer's gradient with respect to A is the derivative of the cost function wait, is this with respect to A? Because we just took the derivative of the cost function. Oh yeah, A, X and A are synonyms. A is just the X and A are synonyms. So why don't I call this with respect to X instead of with respect to A? So the derivative of the cost function in the final layer with respect to X is going to be this, and we figured that out by just the cost function is this thing here. We just take the derivative in the normal way and we get this. This value delta, which is defined as the derivative of the cost function with respect to Z, is this here, by like the definition of a partial derivative. And that's also BP1. So I understand BP1. And it makes sense because you're just looking at the final output layer. So how the cost function changes as a function of the final layer is very straightforward. Then the other BPs are talking about here the inner layers. So BP2 tells you how to get the deltas in the inner layers, and BP3 and 4 tell you how to get the gradients of the bias and the weights from the deltas. So we implemented BP1 to BP4 here, and it actually worked. It lets us classify. But I don't fully understand BP2, 3, and 4. So I'm hoping that we're about to get an explanation, or like a deeper dive into it. So let's get, now that we're done with the recap, let's move on to find out if that's the case. All right, why don't we start right here. A nice consequence of equation 32 is that when the activation A in is small, A in approximately 0, the gradient term derivative of C with respect to W will also tend to be small. In this case, we'll say the weight learns slowly, meaning that it's not changing much during gradient descent. In other words, one consequence of BP4 is that the weights output from low activation neurons learn slowly. Yeah, so the gradient with respect to the weight is the product of delta, which has to do with stuff happening in the later layers, and the activation. So for us, it's the X, but for them, they're calling them A's. So the activation of the node, of the neuron. So if the neuron is giving a low output, that means it's not going to learn quickly because it's not contributing much to the total accuracy, to the total cost. There are other insights along these lines which can be obtained from BP1 to BP4. Let's start by looking at the output layer. Consider the term sigmoid prime of Z in the output layer in BP1. Recall from the graph of the sigmoid function in the last chapter, it's a link to the last chapter, that the sigmoid function becomes very flat when sigmoid of Z in the last layer is approximately 0 or 1. When this occurs, we have sigmoid prime is approximately 0. Yeah, that makes sense. So this graph is this thing here. It's flat close to 0, and it's flat. And this is on the y-axis. So it's flat close to 0, and it's flat close to 1, which means its derivative is close to 0 around those points. And so the lesson is that a weight in the final layer will learn slowly if the output neuron is either low activation, close to 0, or high activation, close to 1. In this case, it's common to say the output neuron has saturated, and as a result, the weight has stopped learning or is learning slowly. Similar remarks hold also for the biases of output neuron. We can obtain similar insights for earlier layers. In particular, note that sigmoid prime of Z terms in BP2. This means that BP2 looks like this. So it's weight matrix of the next layer times delta vector of the next layer, Hadamard product sigmoid prime of this layer. Note the sigmoid prime term in this layer. This means that delta of the inner layer is likely to get small if the neuron is near saturation. And this in turn means that any weights input into a saturated neuron will learn slowly, asterisk. This reasoning won't hold if the weight matrix times the delta vector of the next layer has large enough entries to compensate for the smallness of sigmoid prime, but I'm speaking of the general tendency. Summing up, we've learned that a weight will learn slowly if either the input neuron is low activation or if the output neuron has saturated, i.e. is either high or low activation. None of these observations is too greatly surprising, still they help improve our mental model of what's going on as a neural network learns. Furthermore, we can turn this type of reasoning around. The 4 fundamental equations turn out to hold for any activation function, not just the standard sigmoid function. That's because, as we'll see in a moment, the proofs don't use any special properties of sigmoid. And so we can use these equations to design activation functions which have particular desired learning properties. As an example to give you the idea, suppose we were to choose a non-sigmoid activation function sigmoid, or sigma, so that sigma prime is always positive and never gets close to 0, that would prevent the slowdown of learning that occurs when ordinary sigmoid neurons saturate. Later in the book, we'll see examples where this kind of modification is made to the activation function. Keeping the 4 equations BP1 to BP4 in mind can help explain why such modifications are tried and what impact they can have. So I happen to know that the activation function used in modern neural networks is not sigmoid, but is ReLU. And ReLUs do go up to positive infinity. So I guess, which means their sigmoid prime is basically always 1 when the output's positive and 0 otherwise. Which means it keeps learning forever as long as the output is positive. Interesting. All right, summary, the equations of backpropagation. Yes, we've seen these a few times. All right, problem. Alternate presentation of the equations of backpropagation. I've stated the equations of backpropagation, notably BP1 and BP2, using the Hadamard product. This presentation may be disconcerting if you're unused to the Hadamard product. There's an alternative approach based on conventional matrix multiplication, which some readers may find enlightening. 1. Show that BP1 may be rewritten as delta L equals capital sigma prime of Z of L, gradient A of C. Where capital sigma prime of Z of L is a square matrix whose diagonal entries are the values sigmoid prime of Z of L, and whose off-diagonal entries are 0. Yeah, okay. Note that this matrix acts on grade of C by conventional matrix multiplication. It's so obvious that that's true that I don't want to try to prove it. If it's not obvious to you, just think about what you're doing when you're doing a Hadamard product. When you're doing a Hadamard product, you're multiplying row by row the values together. And what you're doing when you do a matrix multiplication. When you do a matrix multiplication, you multiply one row from the matrix times one value of the vector. And if everything in the row is 0 except for the one number, then that ends up being the same thing. So there's my hand-wavy proof that I'm sure is correct, but I don't want to write down. Number 2, show that BP2 may be rewritten as delta of this. So let BP of 2 looks like this. So instead of the Hadamard product, we did the same thing. It's the exact same. For the same reason, this is the same as that. You just replaced a vector with a Hadamard product with a matrix that has zeros everywhere except where the Hadamard product would have given you a number. 3, by combining observations 1 and 2, show that delta L equals the matrix version of the diagonal matrix version of sigmoid prime of Z times W of L plus 1 transposed times etc., and then you keep going until you get to the last layer. So you just multiply all that stuff together. So why would that be the case? I guess because you keep replacing the deltas. I guess we should look at the 1 and 2 at these formulations, 33 and 34. So you've got this matrix on the left side, and you've got this matrix on the left side. But it's the deltas that so the deltas are on the right side, and this you want to replace with the next one. So you end up like chaining them together into one giant matrix multiplication. For readers comfortable with matrix multiplication, this equation may be easier to understand than BP1 and BP2. The reason I focus on BP1 and BP2 because this approach turns out to be faster to implement numerically. Yeah, because you're just multiplying two numbers together instead of multiplying a whole matrix row by a number. Okay. Proof of the 4 fundamental equations, optional. Aha, okay. So this is what I was missing. I was missing like reasoning for why BP 2 to 4 are true. BP 1 I understand already. We'll now prove the 4 fundamental equations BP 1 to BP 4. All 4 are consequences of the chain rule from multivariable calculus. If you're comfortable with the chain rule, then I strongly encourage you to attempt the derivation yourself before reading on. No, I don't think I'll be doing that. I think I want to attempt to implement things myself. I'm not so worried about inventing the math myself. I want to understand it, but I'm okay with having it explained. Let's begin with equation BP1, which gives an expression for the output error delta of the final layer. To prove this equation, recall that by definition, delta L, or this is the definition of delta in the last layer. It's just the derivative of the cost function with respect to z of the last layer. Applying the chain rule, we can re-express the partial derivative above in terms of partial derivatives with respect to the output activations. Yeah, this is what I was trying to say last time, where you've got the del A on the numerator and the denominator, so they end up canceling, and I didn't have a reason why that's true. I just remembered that that's how that works. Where the sum is over all neurons k in the output layer. Of course, the output activation A of the kth neuron depends only on the weighted input z of the final layer for the jth neuron. When k equals j, it depends on it only when k equals j. And so, derivative of ak with respect to zj vanishes when k is not equal to j. As a result, we can simplify the previous equation to delta L is equal to everything with the same subscript, j. Recalling that A of the final layer is equal to sigmoid of z of the final layer, the second term on the right can be rewritten as sigmoid prime of z of L. Yeah, so this is derivative of the sigmoid of z with respect to z, which just means sigmoid prime of z, which is just BP1 in component form. Next we'll prove BP2, which gives an equation for the error delta in terms of the error in the next layer, delta L plus 1. To do this, we want to rewrite delta L equals derivative of c with respect to z in terms of delta L plus 1 of k equals derivative of c with respect to z of L plus 1 of k. We can do this using the chain rule. So you start with the definition of delta, which is derivative of the cost function with respect to z, which is equal to the sum over k of the derivative of the cost function with respect to z of the next layer times the derivative of z of the next layer with respect to z. Okay. I can get behind this because you've got the two things canceling out again here, so I can get behind that these are the same. Then one of these we know somehow. That would be this one, derivative of c with respect to z of L plus 1. Yes, that is delta L plus 1. So that's what we're replacing the left side here with delta L plus 1. where in the last line we have interchanged the two terms on the right-hand side and substituted the definition of delta L plus 1 to evaluate the first term of the last line. So the first term is the derivative of z of the next layer with respect to z of this layer. So we could substitute the definition of z of the next layer, which is going to be sigmoid of z. Sorry, sigmoid. Wait. Z of the next layer. Z of the next layer is going to be W of the next layer times activation of the last layer plus bias of the next layer. Yeah, Z of the next layer is equal to W of the next layer times activation of the last layer plus bias of the next layer. And then activation of the last layer is sigmoid of Z of the last layer. So we have this thing differentiating. So we want to take the derivative of this with respect to Z. The bias is going to go away when you take the derivative because that's a constant. With respect to Z, it's a constant. So you're going to get, like, W is also a constant with respect to Z. So it's going to be like W times sigmoid prime of Z plus, or maybe it'll just be that. Yeah. Okay, differentiating, we are playing W times sigmoid prime of Z. Substituting back into 42. This one's 42. So yeah, so this is just W times sigmoid prime of Z times delta of the next layer. Boom. Okay, we've understood BP2. The final two equations we want to prove are BP3 and BP4. These also follow from the chain rule in a manner similar to the proofs of the two equations. I leave them to you as an exercise. Prove equations, BP3 and BP4. I don't really want to do that. Let's see if we can just look at it and try to hand wave them. So derivative of C with respect to B. We're going to want to do the chain rule thing, so del C over del B. So the chain rule thing is going to be to put a different denominator here and a different numerator of stuff that we already know. So I think it's going to be like, we always were doing del Z, right? Z. Well, no, for here we put in Z plus 1. For one of the other ones, I thought we put in the activation. Yeah, we put in the activation. I guess we probably want to use BP1 and BP2. Where are they? that's a definition of delta, and BP2 is a definition of delta also. Okay, derivative of C with respect to B. So the things we know already are derivative of C with respect to Z and with respect to A. So why don't we try swapping into Z? So that would be this. Put a Z over here, put a Z over here. So this is equal to delta times derivative of delta with respect to B. So, or sorry, derivative of Z with respect to B. And Z, the definition of that is W times A plus B. So we want to take the derivative of this with respect to B. So this is a constant that goes away, and this becomes 1. But that doesn't make sense, because now I'm saying it's just, oh, actually that's the right answer though, delta, right? BP3. Oh, hell yeah. Okay, so that's the proof of BP3. BP4. What's the form of BP4? We want del C by del W. I'm being really imprecise, by the way. I'm not keeping track of my indices. I would have to keep track of my indices if I were to make a rigorous proof. I'm just trying to do something hand-wavy that convinces me that it makes sense. Okay, so let's do the same trick where we'll put Z in here. So this is W and this is W. So this is going to be delta on the left side times, and then let's swap in the definition of Z right here. The B goes away because it's a constant. This becomes just A. The derivative of W times A, yeah, becomes just A. So delta times A, and BP4 is delta times A. And then I wasn't precise about which layer, but this is, A is from the last layer. Because that's just how this equation works, is W from this layer, A from the last layer. Okay, very cool. Very cool. We actually understand where, we actually understand the whole thing now. I just want to see if I can if I can sum it up in an intuitive way, we're trying to figure out the derivative of the cost function with respect to the things we control. And then we can move the things we control in the direction that will make the cost function even lower. In order to know the derivative of the cost function with respect to stuff, we defined this variable delta, and then we figured out these equations for how to tell the value of the derivative with respect to stuff using delta as this intermediate thing. So will this help me rewrite this code in a nicer to read way now? So I'm calculating all these deltas. In order to calculate the last delta, I needed the last derivative of c with respect to x, which is with respect to a in the math version. Should I just call these A? I think I should just call these, oh, I can't say AS. Okay, we'll call them X's. The X's are the activations. So this is BP1. This is delta of the final layer is equal to the thing. Actually, why don't we finish reading this one last paragraph of this section? That completes the proof of the 4 fundamental equations of backpropagation. The proof may seem complicated, but it's really just the outcome of carefully applying the chain rule. A little less succinctly, we can think of backpropagation as a way of computing the gradient of the cost function by systematically applying the chain rule from multivariable calculus. That's really all there is to backpropagation. The rest is details. True. Now let me go up to the equations. So yes, grad A of C is this thing. Hadamard product sigmoid prime of the last Z is the last delta. Then we go backwards to figure out the rest of the deltas. And then I'm going forwards again to figure out these grads of CW. So first of all, I don't like the names I've given things. Why don't we just call this grad W like we did elsewhere in the code? We're reiterating through these backwards. Or, I mean, these are forwards and these are backwards, but the order we do these doesn't matter. So we might as well do them while we're iterating, right? You have to start with the first one if we do that, though. We're skipping a thing here. That made sense, right? No need for me to explain what the hell I'm talking about. This one is doing one more iteration than this loop. So I was trying to combine the loops, but that would mean I would have to start at len of self.waits. And then only do this, but not do the delta. Alternatively, I could define the same way that I'm starting delta with something in it. I could start grad with something in it. I don't know. I think I might just leave it like this. I think it works well like this. Okay. Okay. I don't know. It didn't really help me write this any better. It seems like it should, though. Just because well, BP3, I don't even have to do anything. That's just returning deltas here. BP4 is doing these products. And that's pretty much as good as you can do them. I could do them inside here, but then I'd have to do one of them outside the loop. Also, I'd have to do them in the opposite order. Alright, I'm happy with that. So we just finished the proof. The backpropagation algorithm. Which we've already seen, but I guess we're recapping. The backpropagation equations provide us with a way of computing the gradient of the cost function. Let's explicitly write this out in the form of an algorithm. Input x, set the corresponding activation a of 1 for the input layer. Feed forward. For each L, 2, 3, up to the final one, compute z equals w times a plus b, and a equals sigmoid of z. So that's this part. Output error delta. Compute the vector delta of the output layer as this. So that's this. Backpropagate the error for each layer from L minus 1 all the way down to 2. Compute delta of L. So that's this. Output, the gradient of the cost function is given by activation times delta is the gradient with respect to the weight, and just delta is the gradient with respect to B. Examining the algorithm, you can see why it's called backpropagation. We compute the error vectors delta L backwards, starting from the final layer. It may seem peculiar that we're going through the network backwards, but if you think about the proof of backpropagation, the backward movement is a consequence of the fact that the cost is a function of outputs from the network. To understand how the cost varies with earlier weights and biases, we need to repeatedly apply the chain rule, working backward through the layers to obtain usable expressions. Exercises. Backpropagation with a single modified neuron. Suppose we modify a single neuron in a feed-forward network so that the output from the neuron is given by f of z basically. The rest of it looks the same. Where f is some function other than the sigmoid. How should we modify the backpropagation algorithm in this case? We modify a single neuron. So in the feed forward, obviously, for that one neuron, you would do something other than sigmoid. So here sigmoid means apply sigmoid to each of the components of this vector. But for that one neuron, we'd be applying sigmoid to all of the components of the vector except for one, and then we'd apply f to that other one. During the backpropagation, if the neuron was in the final layer, then delta L would have a different value at that layer. Instead of taking a sigmoid prime, you'd end up doing something else here. I guess you'd be doing f prime. Just for that one neuron, you do sigmoid prime for the others. And then same here. So I guess you would only change one thing, and then as you backpropagate, the rest of them would still use that result and not have to do anything different. Backpropagation with linear neurons. Suppose we replace the usual nonlinear sigmoid function with sigmoid of z equals z throughout the network. Rewrite the backpropagation algorithm for this case. Okay. So instead of doing sigmoid z, you just do z. Instead of doing sigmoid prime, you just have 1, because the derivative of z with respect to z is just 1. So this just becomes 1, and this just becomes 1. So how well does that do? It doesn't do shit. It's not learning at all. I guess I would have expected it to learn. It's possible that I did something wrong. Yeah, I would expect it to learn, but maybe just not as well. So that's weird. I don't know, and like, he doesn't have a solution, so I don't know. If my answer is wrong, or if that's just what you expect. Yeah, I don't know. It actually seems really odd now that I think about it, because I think the derivative of a ReLU is 1 at all locations, and ReLU is better than sigmoid, like ReLU activation function. ReLU of x is equal to max of 0 and x. So I would think the derivative of that is basically 1 everywhere, because the slope at the 0 part is 1 and the slope at the positive part is 1, and it doesn't really matter what the slope is at the exact center here, I would guess. I mean, what if I did use a ReLU? So what if I literally replaced this with the definition of a ReLU? Return max of 0 and z. I guess that's hard to do as on an array, as a, what do you call it, a pointwise. Can I do np.max? And then sigmoid prime would just be 1. It doesn't like the max thing. How do I do numpy element-wise operation? Element-wise max. Dot maximum or dot fmax. Okay, dot maximum. No, not working. Oh wait, also, I don't know if 1 is allowed here. It's supposed to be a vector. Whatever. I don't know why my implementation of ReLU is not working. We can figure that out later. But I have a feeling this should work, and it's not working for probably the same reason. So I don't know, should I figure it out right now? No, let's leave it for later. As I've described it above, the backpropagation algorithm computes the gradient of the cost function for a single training example c equals cx. In practice, it's common to combine backpropagation with a learning algorithm such as stochastic gradient descent, in which we compute the gradient for many training examples. In particular, given a mini batch of m training examples, the following algorithm applies a gradient descent learning step based on that mini batch. So that he's just going to re-describe the algorithm we've already done. Input a set of training examples. For each training example x, set the corresponding input activation AX1 and perform the following steps. Feed forward. For each L, 2, 3 up to L, compute ZXL equals W times A plus B, and A equals sigmoid of Z. Output error. This is just describing backpropagation. Backpropagate the error. 3, gradient descent. For each L equals L, L minus 1, etc. up to 2, update the weights according to the rule. W of L goes to W of L minus eta over M times the sum of the deltas times activations and the biases according to the rule. So this is one of the outputs from the backprop, and this is the other output from the backprop. Of course, to implement stochastic gradient descent in practice, you also need an outer loop generating mini batches of training examples and an outer loop stepping through the multiple epochs of training. Those for simplicity. The code for backpropagation. Having understood backpropagation in the abstract, we can now understand the code used in the last chapter to implement backpropagation. Recall from that chapter that the code was contained in the update minibatch and backprop methods of the network class. The code for these methods is a direct translation of the algorithm described above. In particular, the update minibatch method updates the network's weights and biases by computing the gradient for the current minibatch of training examples. So we've already gone through this version and our version a few times. Most of the work is done by the line self.backprop, which uses the backprop method to figure out the partial derivatives C with respect to B, C with respect to W. The backprop method follows the algorithm in the last section closely. There's one small change. We used a slightly different approach to indexing the layers. This change is used to take advantage of a feature of Python, namely the use of negative list indices to count backward from the end of a list. So e.g. L of -3 is the third last entry in the list L. The code for backprop is below, together with a few helper functions which are used to compute the sigmoid function, the derivative sigmoid prime, and the derivative of the cost function. With these inclusions, you should be able to understand the code in a self-contained way. If something's tripping you up, you may find it helpful to consult the original description and complete listing of the code. Yeah, so we've already read through this. Forward pass makes perfect sense. The backwards pass makes sense. He's using the negative indices to be able to, well, he calculated the first W outside the loop, even though it's the same as the rest of the W's, so that he can do this in a single iteration, whereas I split it into 2 loops, one to find the deltas and one to find the nabla W's. And then this is the same for us, and then we didn't split cost derivative into a separate function, but I guess we will once we want to swap out different cost functions. Problem: a fully matrix-based approach to backpropagation over a mini-batch. Our implementation of stochastic gradient descent loops over training examples in a mini-batch. It's possible to modify the backpropagation algorithm so that it computes the gradients for all training examples in a mini-batch simultaneously. The idea is that instead of beginning with a single input vector x, we can begin with a matrix x, x1, x2, xm, whose columns are the vectors in the mini-batch. We forward propagate by multiplying by the weight matrices, adding a suitable matrix for the bias term, and applying the sigmoid function everywhere. Okay, we backpropagate along similar lines. Explicitly write out pseudocode for this approach to the backpropagation algorithm, modify network.py so that it uses this fully matrix-based approach. The advantage of this approach is that it takes full advantage of modern libraries for linear algebra. As a result, it can be quite a bit faster than looping over the mini-batch. On my laptop, for example, the speedup is about a factor of 2 when run on the MNIST classification problems like those we considered in the last chapter. In practice, all serious libraries for backpropagation use this fully matrix-based approach or some variant. Okay, so mini-batch. So here you would turn instead of doing this, you turn the whole mini batch into a single X. So X is equal to, and then it's like the columns, you know, x1, x2, x3, these are the columns. So NumPy matrix from vectors you can literally just do this. So x equals np.array this. And what is x1, x2, x3? It's just x for x, y in mini batch. So let's comment this for a second. Well, actually, I want all this stuff. I just don't need to do it in a matrix. So backprop with an uppercase X. Let's make a Y similarly. Y equals this. This is not gonna just work because this should be a ND array. So each of the X's is a matrix now, which is fine. But the result of this is a matrix, so I can't just use B like this. I have to have B be a matrix also. So B equals np.array B for blank in range len of X. Of 0, because I want the number of columns. And then here you can use B. Okay. That's the forward propagation. Then I guess we don't use the B's again. So this might work. Wait, what did it just erase? Oh, I just realigned that. There's no way, right? So it doesn't like my plus B here. So I'm trying to just use the same vector over and over again for B. But is that turning it into... Wait, V stack and H stack. I want H stack or column stack. NP dot, where is it? B. NP dot V stack. I want the same over here, wherever it was. No, H stack. No, V stack. Size 7,840 is different from 784. That just makes me think I'm not stacking it in the right direction. Python, import numpy as np, np.vstack, or how about a equals np.array, a equals np.array123, a.shape, a equals a.reshape 31, okay, np.vstack, a. Okay, that's not what I want. So do I want hstack? I actually do want hstack. Okay. That makes sense, actually. Line 60. So I've calculated them all at the same time, but now when I want to add them to gradient, I can't just do plus equals, because this will be bigger than this, because this has like multiple I want to sum all of the rows. Don't I have the same problem with W? I guess not. Maybe I already end up with the sum for W. But for B, I have to sum the rows. I think I just have to look that up. NumPy sum rows. You can say axis. Okay, so np.sum this guy, axis equals 1. Non-broadcastable output operand with shape 31 doesn't match the broadcast shape 3030. Did it not work? Wait, which one is which? Print grad b of I dot shape. Delta grad b of I dot shape, and also this thing dot shape. Didn't print anything? Why would it not print anything? Clear, run it again. Okay, 30, 1, 30, oh, I have to reshape it, I guess? Because that just never works properly. Reshape to be blah, 1, and the blah is, I guess I can just do grad b of I dot shape. Okay, now remove the print statement. Clear. Wow. Yeah, this is 3 times faster than before, and it still works. That's cool. That's cool. Okay. Yeah, and there's optimizations that could be had here. Like I'm building this matrix over and over and over again. Well, I guess I'm doing it once per layer per mini batch per epoch. Yeah, so I'm building this over and over again. If I already knew what size my mini batches were going to be, I could do it in advance. I guess I don't need this anymore unless like the way I'm doing this is gonna be annoying later. So I guess I'll keep it in a comment. This was for single examples at a time. To do can cache this. Replace with B if doing single examples. Okay. So exercise done, and that was a really cool exercise. In what sense is backpropagation a fast algorithm? In what sense is backpropagation a fast algorithm? To answer this question, let's consider another approach to computing the gradient. Imagine it's the early days of neural networks research. Maybe it's the 1950s or 60s. Maybe you're the first person in the world to think of using gradient descent to learn. But to make the idea work, you need a way of computing the gradient of the cost function. You think back to your knowledge of calculus and decide to see if you can use the chain rule to compute the gradient. But after playing around a bit, the algebra looks complicated and you get discouraged. So you try to find another approach. You decide to regard the cost as a function of the weights, C equals C of W, alone. We'll get back to the biases in a moment. You number the weights, W1, W2, etc., and want to compute derivative of C with respect to Wj for some particular weight Wj. An obvious way of doing that is to use the approximation derivative of C with respect to Wj is approximately equal to C of W plus epsilon Ej minus C of W over epsilon, where epsilon greater than 0 is a small positive number and Ej is the unit vector in the jth direction. In other words, we can estimate the derivative of C with respect to Wj by computing the cost C for two slightly different values of Wj and then applying equation 46. The same idea will let us compute the partial derivatives, C with respect to B with respect to the biases. This approach looks very promising. It's simple conceptually and extremely easy to implement, using just a few lines of code. Certainly it looks much more promising than the idea of using the chain rule to compute the gradient. Unfortunately, while this approach appears promising, when you implement the code it turns out to be extremely slow. To understand why, imagine we have 1,000,000 weights in our network. Then for each distinct weight Wj, we need to compute C of W plus epsilon Ej in order to compute C with respect to Wj. That means that to compute the gradient, we need to compute the cost function 1,000,000 different times, requiring 1,000,000 forward passes through the network, per training example. We need to compute C of W as well, so that's a total of 1,000,001 passes through the network. What's clever about backpropagation is that it enables us to simultaneously compute all the partial derivatives, C with respect to Wj, using just one forward pass through the network, followed by one backwards pass through the network. Roughly speaking, the computational cost of the backward pass is about the same as the forward pass, asterisk. This should be plausible, but it requires some analysis to make a careful statement. It's plausible because the dominant computational cost in the forward pass is multiplying by the weight matrices, while the backwards pass is multiplying by the transpose of the weight matrices. These operations obviously have similar computational costs. Compare that to the 1,000,001 forward passes we needed for the approach based on 46. And even though backpropagation appears superficially more complex than the approach based on 46, it's actually much, much faster. I'm just trying to understand, where did 1,000,000 things come from? It's that Ej is the unit vector in the jth direction. So for each weight, you compute okay, yeah. There's only one Ej for each W because because we're talking about Wj, so it's the J of that W, not of every Ej. Okay, so for each weight you need 2 forward passes, basically. Whereas you get with one forward pass you get all of the weights adjustments with backpropagation. This speedup was first fully appreciated in 1986, and it greatly expanded the range of problems that neural networks could solve. That, in turn, caused a rush of people using neural networks. Of course, backpropagation is not a panacea. Even in the late 1980s, people ran up against limits, especially when attempting to use backpropagation to train deep neural networks, i.e. networks with many hidden layers. Later in the book, we'll see how modern computers and some clever new ideas now make it possible to use backpropagation to train such deep neural networks. Backpropagation, the big picture. As I've explained it, backpropagation presents two mysteries. First, what's the algorithm really doing? We've developed a picture of the error being backpropagated from the output, but can we go any deeper and build up more intuition about what is going on when we do all these matrix and vector multiplications? The second mystery is how someone could ever have discovered backpropagation in the first place. It's one thing to follow the steps in an algorithm, or even to follow the proof that the algorithm works, but that doesn't mean you understand the problem so well that you could have discovered the algorithm in the first place. Is there a plausible line of reasoning that could have led you to discover the backpropagation algorithm? In this section, I'll address both of these mysteries. To improve our intuition about what the algorithm is doing, let's imagine that we've made a small change, delta WLJK, to some weight in the network WLJK. That change in weight will cause a change in the output activation from the corresponding neuron, so delta ALJ. That in turn will cause a change in all the activations in the next layer. Those changes will in turn cause changes in the next layer, and then the next, and so on all the way through to causing a change in the final layer, and then in the cost function. The change delta C in the cost is related to the change WLJK, or the change delta WLJK in the weight by the equation delta C is approximately equal to derivative of C with respect to WLJK times delta WLJK. This suggests that a possible approach to computing derivative of C with respect to WLJK is to carefully track how a small change in WLJK propagates to cause a small change in C. If we can do that, being careful to express everything along the way in terms of easily computable quantities, then we should be able to compute derivative of C with respect to WLJK. Let's try to carry this out. The change delta WLJK causes a small change delta ALJ in the activation of the jth neuron in the Lth layer. This change is given by delta ALJ is approximately equal to derivative of ALJ with respect to WLJK times delta WLJK. The change in activation delta ALJ will cause changes in all the activations in the next layer, i.e. the L+1th layer. We'll concentrate on just the way a single one of those activations is affected, say AL+1Q. In fact, it'll cause the following change. Delta AL+1Q is approximately equal to derivative of AL+1Q with respect to ALJ times delta ALJ. Substituting in the expression from equation 48, we get delta AL+1Q is approximately equal to delta AL+1Q derivative of AL+1Q with respect to ALJ times derivative of ALJ with respect to WLJK times delta WLJK. Of course, the change delta AL+1Q will, in turn, cause changes in the activations in the next layer. In fact, we can imagine a path all the way through the network from WLJK to C, causing a change in the next activation, and finally, a change in the cost of the output. If the path goes through activations ALJ, AL+1Q, etc., to A capital L-1N, A capital LM, then the resulting expression is, I'm not going to read this, but you've just got all these partial derivatives of terms, of A's with respect to their layer that came right before. That is, we've picked up a derivative of A with respect to A type term for each additional neuron we've passed through, as well as the derivative of C with respect to the final activation term at the end. This represents the change in C due to changes in the activations along this particular path through the network. Of course, there's many paths by which a change in WLJK can propagate to affect the cost, and we've been considering just a single path. To compute the total change in C, it is plausible that we should sum over all the possible paths between the weight and the final cost, i.e. delta C is approximately equal to the sum over all of these paths. Where we summed over all possible choices of the intermediate neurons along the path. Comparing with 47, we see that what was 47? What is this? What is what's the difference between this and the next formula? Oh, we Oh, this was delta C, and this is derivative of C with respect to a WLJK. Now equation 53 looks complicated, however it has a nice intuitive interpretation. We're computing the rate of change of C with respect to a weight in the network. What the equation tells us is that every edge between two neurons in the network is associated with a rate factor, which is just the partial derivative of one neuron's activation with respect to the other neuron's activation. The edge from the first weight to the first neuron has a rate factor derivative of ALJ with respect to WLJK. The rate factor for a path is just the product of the rate factors along the path, and the total rate change derivative of C with respect to WLJK is just the sum of the rate factors of all paths from the initial weight to the final cost. This procedure is illustrated here for a single path. What I've been providing up to now is a heuristic argument, a way of thinking about what's going on when you perturb a weight in the network. Let me sketch out a line of thinking you could use to further develop this argument. First, you could derive explicit expressions for all the individual partial derivatives in equation 53. That's easy to do with a bit of calculus. Having done that, you could then try to figure out how to write all the sums over indices as matrix multiplications. This turns out to be tedious and requires some persistence, but not extraordinary insight. After doing all this, and then simplifying as much as possible, what you discover is that you end up with exactly the backpropagation algorithm. And so you can think of the backpropagation algorithm as providing a way of computing the sum over the rate factor for all these paths. Or, to put it slightly differently, the backpropagation algorithm is a clever way of keeping track of small perturbations to the weights and biases as they propagate through the network, reach the output, and then affect the cost. Now, I'm not going to work through all this here. It's messy and requires considerable care to work through all the details. If you're up for the challenge, you may enjoy attempting it. No thanks. And even if not, I hope this line of thinking gives you some insight into what backpropagation is accomplishing. Yeah, I think it does. I think it does. It's basically like, once we had the idea of delta at each layer, then we were able to come up with expression for like ways of calculating derivative of C with respect to W and with respect to B. And this is saying, here's how you could have come up with the concept of the deltas. It's just by keeping track of this gigantic sum of all of the terms in the cost function when you change one thing. If you did that, you would, and then like you tried to simplify it, you'd end up with matrices that compute delta, basically. So it's a way of doing it without any matrix multiplication. You just try to figure out how to turn it into a matrix multiplication, and you would find what we found. What about the other mystery, how backpropagation could have been discovered in the first place? In fact, if you follow the approach I just sketched, you will discover a proof of backpropagation. Unfortunately, the proof is quite a bit longer and more complicated than the one I described earlier in this chapter. So, how was that short but more mysterious proof discovered? What you find when you write out all the details of the long proof is that after the fact, there are several obvious implications staring you in the face. You make those implications, get a shorter proof and write it out, and then several more obvious implications jump out, so you repeat again. The result of your few iterations is the proof we saw earlier. Short but somewhat obscure because all the signposts to its construction have been removed. I am of course asking you to trust me on this, but there really is no great mystery to the origin of the earlier proof. It's just a lot of hard work simplifying the proof I've sketched in this section. Footnote: there is one clever step required. In equation 53, the intermediate variables are activations like A of L plus 1Q. The clever idea is to switch to using weighted inputs like Z of L plus 1Q as the intermediate variables. If you don't have this idea and instead continue using the activations, the proof you obtain thus turns out to be slightly more complex than the proof given in the previous chapter. That also makes sense, because that's the other. That's the other non-obvious thing, I guess, is that keeping track of activations makes sense. Computing delta doesn't make sense, or I mean, it makes sense, but it's not obvious how I would have thought of this unless I did it the long way and then found that there's this value delta that if I had, I could just do matrix multiplication. And Z is the same. Like, it's not obvious in advance that you need to keep track of z's separately from the x's, but I think that would jump out at you once you, I guess he's claiming that would jump out at you. No, it wouldn't jump out at you. It's a clever idea, so you wouldn't be able to think of it. Okay. We're done with chapter 2. We're going to end here for today. Next time we're going to do chapter 3, improving the way neural networks learn. Thanks for watching.